against his whole team, and just a lot of different storylines that I think are great. We had this in the 2000s, the seeds of it, when Shaq went to Miami, but Kobe's Lakers team wasn't good enough. We had the seeds of it when Durant went to Golden State in 2016, and then there was going to be an OKC Golden State rivalry, but Golden State was just way better than OKC. This has a chance to be a really fun back and forth. Every time they play, it's going to be a fun game like the one tonight, and I'm looking forward to it. I would say for the rest of the 2020s, this is our best bet for an awesome NBA rivalry. Like Boston, Cleveland, maybe that'll get there. I doubt we're going to have all the storylines and the baggage that this one has. Minnesota, OKC, sure. SGA, Anthony Edwards, that'll be great. Can't wait to watch those guys battle, but it's not going to have the baggage in the history of this rivalry. So depending on how long LeBron is able to play at this level, this is the best we're going to do. Could we get this as a 2-7 matchup in the NBA playoffs? So Lakers right now, 35 and 21. 2 seed is conceivable for them. Dallas right now is the 8 seed. There's a bunch of teams tied in between 7 and 10. They're getting some guys back soon. If you want to get good ratings NBA, I would rig a 2-7 Lakers Dallas. I think would be the way to do it. Anyway, this is an awesome rivalry. That was my first takeaway tonight watching this. Where I'm just like, this is must-watch TV every time these two teams play. Second one is the Lakers, who Rousseau and I talked about on Sunday night. I think they're a wild card contender. They're not one of the 4 contenders to win the title, but they might be 5th. And they're definitely I don't know what the ceiling is of this team yet. They're 15 and 4 in their last 19 now. They've been top 5 net the whole time. Rui at center, which, they've done from time to time when AD was out, but they're doing it by necessity now because the Mark Williams trade got canceled. He's a little Karl-Anthony Towns this year at times, and I mean that in a good way. Like, he's got size, he can stretch the floor, and he's just big enough that he can push against a post-up player. Not a rim protector, neither is Towns. But when you watch them, and it's their crunch time today, and I think their crunch time just going forward, Reeves as the point guard, even though he's not a point guard. Rui as the center, even though he's not a center. And then LeBron and Luka and Finney-Smith as the wings. And they're all just really smart basketball players who can kind of fill in the blanks and not totally get burned. The rim protection's not going to be perfect. There's going to be guards like Kyrie tonight that they're just not going to be able to stay in front of unless it's a team defensive concept. I think it works. I'm bullish on this Lakers team as a contender. Everyone's like, oh, you hate the Lakers, When the Lakers are good, I'm going to admit it. We were admitting it. We were doing pods all the way up until COVID happened in the 2019-20 season saying the Lakers Clippers were the 2 best teams. I think the Lakers are a legit contender. And I think they can get away with these goofy lineups because they're really well coached and their best 2 players are really smart and know where to go and what to do. So that's my second takeaway. Ironically, Luka's not in any of my big 3 takeaways because we know how talented he is. We know how good he is. And, it was interesting. You would have bet, like, if you're betting on FanDuel, you're doing like the same game, the parlay boost token. The obvious bet would have been, oh, Luka, revenge, points. And it never works out that way. He just did the classic other version of a Luka game where he filled out every part of the box score, got a triple-double, but, he did not have the 40-point game, which I think, when you think about revenge, it wasn't what we saw tonight, but he played a really smart offensive game and really controlled it and did a lot of good stuff. But that leads to the third thing.
This meeting is being recorded.
All right, so let's get started. Good morning and welcome back to Computer Architecture. So we'll continue Chapter 3, which we started this week, and Chapter 2 homework is due tonight. All right, so oops, yes. So when we left off, Monday we covered integer operations and a start on some multimedia operations that are also integer based, basically the vector or SIMD type instructions. And then we talked about the floating point representation. And so when we ended up, we had talked about the major components, a floating point example, some special cases, such as being able to get close to 0, which helps out with doing comparisons of floating point numbers, older standards. And then we also want to have representations of error cases. And so that is supported as part of the IEEE standard. So now that we've covered representation, single and double precision, let's look at the steps necessary for doing some floating point operations. So let's start out with a decimal. If I take a look, I have 9.999 to the 10th, and to 10 to the negative 1 power, I have 1.610. So first of all, they are in normal or normalized notation. But what that then means in this case is when we want to add them together, we need to align the decimal points. So we need to shift the exponents. So we get the exponents lined up. And now that the exponents match, we can add the significance, the fractional bit, and get our new significand. We then look at our new significand, and it is not normalized. So we'll fix that. 1.0015. We can't add to the accuracy of our solution. So we can only maintain what we started with. And we started with 3 decimal places. So we will round, check for overflow, underflow. We'll normalize it. It's no longer 3 places. We have 4 decimal places. So we'll round those. And, if it was like 9.99999 and we had to round, we'd end up with 10. So we might have to renormalize. I think there's another example of that. So we are doing some shifting and we're doing some addition, right, for our addition. So it's similar in a way to integer operations in the type of hardware we need, but there are more steps involved because of the complexity of the representation, right? So let's change this to binary. In binary, it works much the same way. I align the binary points, because here I had 2 to the -1 versus 2 to the -2. I add the significance. I normalize the result, check to see if overflow or underflow, and then I round it. In this case, no change was needed, and so I'm good to go. So there's also this rounding step and this normalization step that has to occur after we've done all the math, right? So to be able to, basically we got to bring the number into our system, do the math, and then store it back out in the correct format, right? And so we've got these 2 extra steps that aren't automatically taken care of by the math hardware. So the main takeaway is this takes more than a single clock cycle. In fact, let's see how long it took, for example, on that older x86 architecture, because they did have the clock cycles because they were trying to compare and contrast. So we can see that the ARM architecture, everything is under the RISC model. Everything is tried to make a simple instruction, not a lot of power or steps to the instruction. So all of these instructions have been designed to run in a single clock cycle. That's not really true anymore. And the other thing to take a look at is this only has an integer addition subtraction. There is no floating point operations or multiplication division. So over here, this has got 10 more years of growth on it. And it doesn't include integer operation or float operations. What it has is integer operations. But if we take a look, for example, comparing integer subtraction or integer addition, where's add? They take a bit more clock cycles, but they're more powerful instructions. So they can also move stuff from memory. Whereas multiply and divide take up more clock cycles. So one thing that happens here is we'll run this in parallel with the regular CPU operations. So what I can do is I can sort of start the floating point operations. I will take advantage in a modern CPU that is pipeline, so I can do overlapping if I have a bunch of floating point operations to commence. I'm not going to slow down the clock. I'm going to keep it running. And what I'll also do is I'll have a separate set of registers just for floating point operations. So I have my general purpose registers and I'll have my floating point registers. And the assembler will take care of mapping between, right? So the assembler will know and the hardware will know that if I'm doing a floating point operation, I'm using the floating point registers. If I'm doing an integer or regular operation, I'm using the regular general purpose registers. We can also see that there are components of what we're seeing before was integer operations, but there's vastly more steps. We still have 2 source registers and a destination register. We have some control logic, which will get even more complex. And we have an arithmetic logic unit. And remember, to do multiplication and division with our multiplication with integers, we might have multiple floating point units, but they'll be sort of off to their own multiple ALU units, sorry, but they'll be off running in parallel. So this has in parallel a big ALU and a small ALU. The small ALU helps out with doing comparisons because what we'll see in chapter 4 is one of the other purposes of the ALU is, right, if we looked and remember from chapter 2, one way we did comparisons to see if it's 0 or not 0 was subtract one number from another and see if the result is 0. So that's arithmetic logic unit. So here we'll see if the exponents match. If they don't, then we will shift them. Shift right, the smaller one, whichever one that happens to be. So we map both the exponents into here, and then we bring the exponents in and we shift them. For the fractional bit, we feed them both into the big ALU, which does the addition of the fractional bits, which have also been shifted. Then, once we're done with the results, and we can detect as part of the ALU overflow, we'll take those results, we'll shift them, we'll line up our exponent, we'll do the rounding. We may have to repeat this, and then we write it out to the destination register. This is all well known. It just takes more work to make it happen. So floating point operations are slower. Okay, so let's take a look at, and subtraction, as we saw with integer operations, is pretty much the same thing as addition. Okay, so floating point multiplication. In this case, we're going to combine the exponents. So we're going to add them together. The problem with our IEEE standard is we've got a bias introduced in there to keep the numbers positive. And so we need to remove the bias in a bias one. Here we're doing decimals, so we'll save that for the next slide. And now we do the multiplication of, the significance. And we have our new number. Our new number is not normalized, so we'll normalize it. Check for underflow, overflow. Then we'll round it. In this case, we simply could drop a digit. And we'll fix the sign, right? These are two positive numbers, so we end up with a positive number. And we're all good. Let's do the binary example and add back and also address the issue of bias. So the example up here on the first bullet has no bias. -1 and -2, those are obviously not biased because they're negative values. But a bias value would have been 126 plus 125, which would be too big. So we'll subtract one step of bias out and get us our new value, -3 plus 127 for the correct bias. We'll do the multiplication of the significance. We will normalize. In this case, no additional bits were added, so no change. We didn't have to do anything for rounding, so no change. We fixed the sign, and we're good to go. It feels like some of this is the same, but there is an additional complexity because instead of doing addition, we're doing multiplication. And instead of merely shifting, we're doing some adding. We can use the floating point adder. One way to look at this would be that this would instead become its own loop because our multiplication is multiple passes of adding in order to make that happen. But essentially, we can use the same hardware to do all this. And if we've already devoted this much hardware to do all this, then we will also do the square root. We will have it handle floating point to integer, integer to floating point for conversions. And we will also incorporate trigonometry functions and log functions, and whatever else that you see in the standard math libraries of programming languages. We'll put this in hardware rather than doing this in software because it'll be faster. Chapter 4 will talk about pipelining. And so there are ways to speed this all up. This is additional hardware to the regular CPU, so we can also run this in parallel. So I can farm out, as I mentioned, we'll have floating point and general purpose registers. So I'll farm out the floating point operations to the floating point unit. In older machines, like this original ARM architecture version 1, it has no floating point support in the hardware, so all floating point operations had to be done in software, which would have been extremely slow. And for those floating point registers, we can either reference, there'll be 64 bits. And so we can either have D for our double precision filling the 64 bits, or the single precision will fill the lower 32 bits of our 64 bits. And the assembler will take care of this, right? If I'm multiplying two floats or a float integer, then I'm going to have to convert the integer to a float. I'm going to do a float multiplication. I'm going to pass the values over to the float registers. The floating point unit will be off to the parallel, do its work, and then put it together again, right? And all of this is possible because of Moore's law and, being able to double the transistors. So if I have twice as many transistors, well, I already figured out how many transistors I need for my CPU. So I'll use the other doubled number of transistors to do a floating point unit. 2 years later, I'll add a GPU to it. 2 years later, I'll add a more powerful GPU unit to it. 2 years later, I'll add a second core, right? And so that's where we see this growth as the size of the transistors shrink and the speed doesn't go up as much. It does also mean that the number of instructions I have balloons, right? So now I've got add and subtract, multiply and divide for unsigned and signed integers. And then I have them for single precision and double precision values. On top of that was a register-to-register based architecture like the RISC architecture of ARM. I also need to have separate load and stores for doubles and singles, and then the regular load and stores that are doing bytes and half words and doubles and everything else. And that's essentially what we're seeing here on this slide right here. We can also do comparisons, right? I tell you to kind of avoid this or to be very, very careful when you're doing comparisons of floating points because you will get rounding errors over time as you do operations on floating point values. Having said that, though, if you go to the Wikipedia page, they do have a design rationale there. And he mentions, so William Kahan, he's an Intel engineer, right? And so he did the Intel implementation for floating point, and they were one of the primary leads on the IEEE standard. And so he says that we design our floating point arithmetic to be moderately tolerant of well-meaning ignorance among programmers. They wrote the floating point standard with the recognition that there'll be people who want to use floating point, but they're not necessarily well-versed in the ins and outs of representing floating point on computer hardware, nor are they that depth into numerical analysis or some of the other mathematical aspects of what's occurring here. They just want to be able to use it and expect that it works correctly, right? And so that's the focus here. He points out here, for example, the loss of an Ariane 5 rocket because they did a conversion that didn't use the standard IEEE floating point policy. And they converted a floating point to 16-bit, had an underflow error, and they lost, what was it? An integer overflow. Exception handling was inappropriate. The rocket veered off course and came apart from the forces as it veered off course. And that's a couple of $100 million. So fortunately, we're not doing things that are that explosive or that expensive in this course, but it's something to be aware of when you get out there in the world, depending on where you go to work. All right. So we've got our arithmetic, our comparisons, our load and stores. We've got our floating point registers, our floating point unit. We're basically added all of this capability to our regular integer general purpose unit. Okay, so let's try it out. So here we go. Floating point example. I'm going to do a Fahrenheit to Celsius conversion. So I'm returning a float. I'm passing in a float. Now, what you'll see is what they do is they map the registers sort of in a one-to-one correspondence. So there aren't more floating point registers than general purpose registers. There's still 32. 32 in the modern architecture for general purpose, 32 for double purpose. So I don't have to change the format of the instruction. All right, I can still keep the format instructions. I still have 5 bits for the ID of my register, and all of this still works. So even though I'm using floating point registers, I'm still going to follow similar conventions, such as 0 through 7 are being used as arguments for a function call. So we've got one argument here, 0, and that will be our input or parameter for our float routine. And so we've got our numbers, and there's a bunch of literals in here. So what'll happen is the compiler will sort of pre-compute these literals and store them in a memory location so that they can be accessed by the program, even though you didn't really declare a memory location for 5, 9, and 32. So 5, 9, and 32 are stored in the proper format somewhere that because I can't embed them in the instruction because they're floating point data types. So what I need to do is load 5 and 9 into single precision registers. I will do the division. Then I will load in 32, do the subtraction, and then do the multiplication, and we'll put the results back in the return register, which the convention is to use 0. And oops. Then I return back. So any questions on that basic process or the differences between floating point and integer operations? Okay. All right, so let's do an array example. And we're gonna revisit some array examples throughout the remaining chapters of the textbook, because he'll use this as a way to demonstrate performance enhancements across the different chapters. But first of all, we'll start off small. So what I want to do is a basic array multiplication and addition here. These types of operations are common enough in kinematics and physics operations and graphics operations that there are array or matricy operations. I remember using these a long time ago in a project with some 3D modeling. We're going to have a lot of precision, so we just use double precision elements. And so we've got 3 multi-dimensional arrays, 2-dimensional arrays, X, Y, and Z, and we'll put the result back in one of those arrays, X in this case. We're going to use integers for our indexing, right? Because the array elements are whole numbers for indexing purposes. And in this case, we've hard-coded the size of the array in this example, 32 by 32. So we'll loop through our arrays, and then once we get all the way in, we'll pull the elements, multiply, add them, and store it back out again. All right. From our perspective as a C programmer, a high-level programmer, we've got about 5 lines of code, a declaration, 3 for loops, and the body of the inner for loop. And the author skipped all the curly braces to save space. So addressing is integer based. So we're going to use general purpose registers for that. So all of the addresses and registers down here are all the general purpose registers, right? X0 through 2 for the array, the base of the 3 arrays. And I, J, and K will use a persistent or more long-term register 19 through 21. So we can generate some offsets as we work our way through. We can do the addition here and the logical shift left are reaching into the arrays and getting the individual array elements and putting them in there. And L1, L2, and L3 are, the JK and I loops. And so we initialize I to 0, then J and K. And then finally down here, we've got a floating point operation in the sense that we're doing a floating point load, right? A double load from one of the arrays, then do all the address calculation to get an element from the second array, then get the third array. So now we've got in 16, 4, and 18 are elements. We'll do the multiplication, the addition. Again, we're using floating point array or registers and floating point operations. Then we'll increment, add I, our indexes, K, J, and I. And before we finish here, we'll store the results of our multiplication back out to the destination array location. And again, we're using a floating point store versus the regular store. Test on the array index to see if we're done yet, and then keep going. So what have we got? Like about 30, 35 lines of code in assembler to do about 5 lines of C code. Plus, you're having to do all of the low-level work for mapping elements in the arrays, bringing them in, doing the math, and putting them back out again. Very tedious. Okay, so that's our example of doing a floating point operation using our floating point hardware incorporated as part of our modern CPU. The IEEE standard also, in addition to doing some error handling and having different sizes and how you specify those sizes, you can go with more bits precision. So ground, guard, round, and sticky are the names for those. You can also do some choices on our rounding modes and fine-tune the numerical behavior of a computation, right? Not every floating point unit does this. You can have a set of defaults, and that works for probably 99% of the people, and we just run there. Because typically what happens is if I want to incorporate extra bits precision, I want to have more than just some standard rounding modes. I have to implement that in hardware. So that's going to increase the cost of my floating point unit. Additionally, it may or may not potentially slow things down. And if I'm trying to compare my chip to other people's chips, I may not want to do that because I don't want to slow down and therefore have a worse performing chip than other people. So let me see if I can find it. All right, so precision. There we go. So comparisons and roundings, right? So for roundings, just to show you an example, we can round towards 0. Actually, the other Wikipedia page has a better demonstration of this because they have a little table, right? Here we go. Let me share that tab instead. Okay, so we can round toward 0, positive infinity, negative infinity. We can round to the nearest, ties to even, nearest ties away from 0. So like 11.5, I'm rounding away from 0. 12.5. Then in the negative value, I'm again rounding away from 0. Whereas here, ties to even, I'd come down toward zero, toward its infinity, positive infinity, and negative infinity. So any questions so far? Everybody up to speed? All right. So we've done integers. We discussed supporting multimedia operations, and now we're done floating point. So let's revisit multimedia operations. All right. So another name for this is subword parallelism, because typically we're going below the size of a word, right? 32 bits, so we're going 16 bits or 8 bits, or we could go 32 bits. The other thing that happens is this will be yet another component as part of our chip. So now we'll have a CPU, we'll have a floating point unit, and we'll have this vector unit, right? And so these can all run in parallel. And we will add yet another set of registers. They'll be 32 in number, so we don't break the format of our instructions. But we may want to make it even wider than our regular 64-bit. 64-bit, we didn't have to expand on that for floating point because nobody really does 128-bit floating point. They just do 64-bit or 32-bit. But if I double or quadruple my adder, then I can have 128-bit or 256 bits. And I can just do a lot more 8-bit values. This is very useful because typically if I'm doing graphics or audio, I'm not doing one picture or one, snapshot of a sound. I'm doing a stream, right? I'm doing multiple frames of video. I'm doing multiple seconds, minutes, hours of audio. So I'm streaming in a lot of data, whether that's coming from the hard drive or secondary storage or the network or wherever it might be. And so I'm going to continuously be streaming in. So again, we won't exceed the number of registers that we can already map to in our instruction set, so 32. We will have 128-bit registers. They will accept floats and ints. So our SIMD instructions will include both integer and float operations. So I can do floating point adds, in this case, across 4 singles in a 128-bit register. Or I could alternatively do a bunch of integer adds, such as 16 8-bit integer adds. This will come out of a library that you're using, a multimedia library, which will have mappings to these, and then the compiler will fill in the details and select the actual encoding for the instructions to make all this happen. So out of those 1,000 instructions that we now have in the ARM architecture, a quarter of them are just these SIMD instructions. As you saw in the example here, addition, multiplication on the array, these types of dual operations, or fused operations is what they call them, are common enough that we'll have those built in as a complete instruction. So rather than actually issue a multiply addition, I have a fuse multiply add, a fuse multiply subtract. It'll do both steps as part of a single instruction. Conversions, scalars, square roots. I'm doing a lot of array-based operations because data is collected in sets. So strided or structured loading across rows and columns of my arrays so that they can be efficiently mapped through the cache system. So we'll revisit this idea in chapter 5. And of course, this is multimedia type operations. So we will support our saturating arithmetic mode in that we basically ignore overflow. We simply cap out the number at the maximum number of bits. Okay. As I mentioned, Intel was one of the primary leads in the IEEE standard because it was 1985. And so in the 1980s, Intel was looking at incorporating floating point into their chips because they were selling to the PC market and they wanted to make the PCs better and more competitive against more expensive chips and supercomputers and mainframes and so forth. And so the way they initially incorporated this is on the motherboard, they had a separate second socket, and that would be a floating point unit. The benefits of that is it was still difficult and slow to access from memory and the hard drive. So when I pulled values in from memory, I could shunt them across to the math coprocessor and not interfere with my bus to my CPU. And the CPU would have the controlling logic, and the floating point unit would have where we started out with, and we mentioned for the ARM architecture, its own set of registers. The other thing that they did was instead of 64 bits, they did 80 bits. This allowed them to incorporate, was pretty good performance, more levels of precision. So they could incorporate these extra bits of precision, such as the guard and round and sticky. And basically, over multiple math operations, keep the level of precision pretty uniform across them. This was in the Intel model, they sort of also treat the stack or the registers as a stack. So then I can push things on and off these registers by using some combination operations. In memory, we're going to be pulling a 32-bit or 64-bit. So as we pull it in, it becomes an 80-bit. We do the operations, and then we put it back out again. This worked. It didn't work as well as vastly more expensive hardware, which, makes sense. But it did work much better than implementing this in software. Let's see if I can find. Yeah. So here's what we end up with is this is a separate floating point unit chip. A lot of this regular portions would be the registers as part of the unit. And then the things that look more irregular are, the actual computational units as part of this chip. And this version post-dates the standard. So it was made to be compliant with the standard once everybody argued out the points. It was also designed to be much improved over the earlier generation, the 8087, 8287, 1987. So $500 just for a floating point if you buy 100 of them each, right? Retail, $800. And I think that was the 16 megahertz. So 25 megahertz, $1,400 back in 1987. So that was more than you could buy a complete computer for $1,400, right? right? Back in 1981 and through 87, the introductory price for an IBM PC with keyboard and monitor was $1,500. Of course, this did not come with a floating point unit, and it just did the basic business operations, which wouldn't really include like a spreadsheet. But Excel spreadsheet didn't exist at the time. So this was a starting point, and it had basic limitations, but it worked well enough. '87 is still predating the ARM architecture. And the ARM version 1, as I mentioned before, no floating point. So when they added it a few generations later, by that time, the cost of the manufacturing and transistors had dropped enough that for ARM, they never had to do it that way. Everything was combined. So one of the differences with the x86, the more complex instruction set from the x86, is their handling of other locations for storing the data. So unlike the register-to-register operations of the ARM architecture, I can reference the registers as a stack. I can reference memory operations or memory locations. And we can see that I can go from memory to the stack, which is then a mapping of my 8 registers, far fewer registers than what the ARM architecture started out with, which was 15. I've got integer and floating point data transfer. I've got arithmetic operations, which can work from memory and not just register to register. I have a square root operation, an absolute operation, some conversion operations. I've got comparison operations, and I've got the transcendental, the arctangent, the cosine, sine, tangent, and all of those basic operations as part of my chip architecture, of my floating point instruction set. And then, let's see. And then for the multimedia part of the Intel Empire, or x86 architecture, they also had larger registers, 128-bit. I think nowadays they use 256 bits. And 4 in the 32-bit, and they've gone through multiple versions of this. So here, this one lists SSE2, and it's still not the latest one. But it, again, just like the ARM architecture, supports integer, the multimedia type operations, our vector, our subword parallelism. When it was 64 bits for the CPU, then we got the full number of registers that we could work with. And we could additionally do floating point. And with 128 bits, I can do 4 floating points. So then this is where the pipeline and being able to just have, Moore's law, more transistors, and of course, the increase in speed to make this all work. And we have our modern architecture. I think what I'll do is just stop a few minutes early today and pick up fresh on Monday the matrix multiplication example. And then we'll also do a whole bunch of assembly code next week focused on doing math operations of various kinds, plus doing some function calls and stuff. So unless you have any questions about chapter 2, we'll just stop here. And I will have a good weekend, at least a much warmer weekend. And I will see you next Monday.
watching LeBron reinvent himself on the fly, and I think this is his 22nd NBA season at age 40, when we thought we had seen every version of whatever was happening with him, I didn't think he ever had a chance to compete for a title again. And almost immediately, he has figured out how to kind of coexist with Luka, how to let Luka have the ball way more than we've ever seen LeBron be comfortable with a teammate since 2011 Miami, playing off the ball and figuring out how to affect the game in all these different ways. And then when he gets the ball, doing LeBron things. This is a hybrid of 2011 Miami, that first year, when it was still Wade's team, and he was kind of easing his way into it. He was still getting his stats, but there was a lot of time when Wade was cooking because Wade was one of the 3 best players in the league. And he's deferring to Luka, at least what we've seen so far, while also trying to figure out all these different ways to fit in. Like he'll get like these sneaky offensive rebounds. He only 2 assists today because he didn't have the ball that much, but he still ended up with, I think he had 25 and 12, got some big rebounds. And then defensively, the first, 2 months of the season, he was just atrocious defensively, and all the advanced metrics backed it up. And he's been way more active, and I'm just really impressed. The defensive rebounding, the off the 100 stuff. And, after the second month of the season, I didn't think there was any case for him to be a top 25 player anymore. I don't think there's 9 players playing better than him right now. Like you go Jokic, SGA, Giannis, Tatum, those 4. Luka from a pedigree has to be still a top 10 player. Mitchell, Brunson, Edwards. And then it's LeBron and Cade are probably the 10 best players in the league right now. There's been some injuries. We've lost some guys. But LeBron has to be in the top 10. And I think he's a second team All-NBA guy the way this is going. He's been awesome. And, at this point in his career, when he's done pretty much everything he could do, and we see a lot of the old superstars, they'll call
Rockets took care of the Bucks yesterday, 173 and 11, man. Hey, that Rockets team, man, them young boys, they can hoop, man. They're very entertaining basketball right now. Like across the board, like with a young team, you see a lot of rookie mistakes sometimes and it's clutch situations, but they play a really good brand of basketball, man.
Yeah, they remind me of OKC last year. We was fans of OKC.
I like that.
We liked them. They was exciting for the year, playoff time. They just didn't have that experience. And I think that's gonna be the same thing for the Rockets.
Yep.
But they're a good team though.
For sure, man.
Great future team.
Man, who would you say is the best player on this Rockets team?
Jalen Green.
Okay.
I think they collab well. Like I think Thompson Twin is special. Jalen Green is probably the highlight player. He's probably the most explosive player they got offensively. But the best player is obviously, I don't even know how to say his name. I ain't going to butcher it. The center. Yeah. He makes a lot happen for that team.
Yeah.
But Jalen Green's the most explosive player.
For sure. I only asked that question because I wonder next year how that answer will go. Because if Thompson takes another leap like he did this year.
No, they just got to get that experience, bro. They're going to be okay. Houston is in good hands if they can find a way to keep those players together.
Yeah.
They'll build like OKC, like bro said. They glad to see teams like that, bro.
Yeah. What do you think they do with Van Fleet next year? Do they
Whatever he
get no
wanna
balls
do.
or?
I don't think they trust Reed Shepard yet. He probably gonna be one of them guys to get a chance next year. Get a little more minutes. I think they're gonna give him that same Peyton Pritchard type of treatment. He gonna
Which
play.
is good.
He gonna play a little bit second year, third year, get a play. Keep him for a low number or 4 years, 32.
You can just trust Fred more.
For sure.
Yeah.
I want to ask you about this player yesterday. Thompson got ejected for this. Y'all feel like this is a flavor too?
Yeah, he wild.
That he's out
I
of
didn't say that motherfucker. Blow it up. My fault.
Yeah, you can't grab around nobody's neck, bro. You wild.
What he do? He did that to Giannis. That's cool. He's playing hard, boy. Too much of the ATL in you, boy.
Nah,
That's a hard foul. Giannis must have said something to him.
Hey, with 2 hands around the neck too. I think that's what got him ejected.
He acting like a boy from the Pistons. Crashing out.
Isaiah Stewart.
Yeah.
He's out of there.
They was just like,
Oh,
man.
look at there.
Look at this.
V-neck hairline. I hate that fucking mustache.
I hate him.
Oh, we know you hate. I hate that brother.
Team builder, we got Jump Tony Brothers. That's tough,
I
man.
love that young dude though, man.
That's tough. But a lot of people just like, that should have been Flaker too. It's like the 90s have been a playoff. Well, niggas not 90s.
Nah, you can't do that. But I love his energy though, bro. He got a lot of dog in him, man. That team is in good hands for sure.
For sure, man. Last but not least about this, man. The Bucks, obviously, if they don't get to conference finals, it's time to blow it up, right? Everybody got to go?
Y'all let y'all talk about that. I don't like all this blowing teams up shit. I don't be knowing, bro.
Yeah, it just don't make sense.
I think everybody just gonna rock out.
It's a waste. Yeah, you can't make it to the conference finals or the championship. It's time to go in a different direction.
Who you getting rid of first?
Obviously, Dame got to go. You got to trade Dame. You got to get younger.
Okay. Yeah,
You
for the future.
Giannis might want to explore something different. So,
Lord Jesus, where does he even
they
go?
won in 2021.
Exactly why they're saying what they're
2025.
saying.
Really...
Give the crazies all of California. It's already land of fruits and nuts. Yeah, we can give them California. I'm fine with that. They can live in LA. That's fine.
It has been 1 month since Southern California exploded in a fierce fire
They can have
tore through
that.
the Palisades and beyond. Just a few hours later, on the other side of LA County,
fine with me.
another deadly fire breaks out, the Eaton Fire. It raced across Altadena and Pasadena. The two fires charred more than 37,000
Right there.
acres.
They can all live-
destroyed
that sounds
over
like a lovely
16,000
community.
structures and cost 29 people their lives.
Too bad it didn't cause the right people their lives.